Today is our second lecture on the coordination chemistry. Last lecture it was introduction to the coordination chemistry, and as you know it, I gave differences between the coordination compounds and the double salts. Now today our lecture will be on the basic terms that we use in coordination chemistry regarding the coordination compounds. I have here given an example of a coordination compound, which is copper ammonium sulfate. And most of the terms are written in this coordination compound. One is the central metal ion. Every coordination compound contains a nucleus, at least one. And that nucleus is the central metal ion, and here that central metal ion is copper. We'll be taking each term in detail. Let me first introduce all the terms, more basic terms, which we use in coordination compounds. The first term is the central metal ion. Then the central metal ion has a charge, which is called as oxidation number. Here I have written Roman number, which is second. Second in Arabic numerals means +2. In your 11th class, there's a chapter called redox reactions. There we have calculated the rule. You have used the rules for calculating the oxidation number of an element in a compound. If the oxidation number of an element is positive, then we can express that positive oxidation number in Roman numerals. That expressing positive oxidation number in Roman numbers, you call it a stock notation. So stock notation for +2 oxidation state is second. Stock notation plus +1 oxidation number, or +1, whether you call it as oxidation number or you call it as oxidation state, it is the same thing. +2 means first. +1 is first. If it is +3, then we use the term third, and so on. But this stock notation is only used for positive oxidation state. Negative oxidation state has no stock notation. If in a compound oxidation state is -1, you have to write it as -1. But in positive oxidation state, we'll be using Roman number. So central metal ion in a coordination compound has two characteristics. One is its oxidation number, which in this compound is +2, and we will be calculating this oxidation number, how it is +2 in this coordination compound, similarly other coordination compounds. Then this coordination number has one more, central metal ion has one more property, which is called its coordination number. And in this compound, in this coordination compound, copper has a coordination number of 4. Again, this term will be taken in detail. What is coordination number and how do you calculate the coordination number? So central metal ion has two characteristics. Rather, it has two numbers. One is oxidation number, another is coordination number. Now, related to coordination number, there is one more very, very important term, which is the ligand. And this compound, NH3 ammonia, is a ligand. Again, when we take this term ligand in detail, you will come to know what is a ligand and how do you classify these ligands. Which means this coordination number, which is the property of central metal ion, is related to the ligand. Okay. Then this central metal ion and these 4 ammonia molecules are put within square brackets. This square bracket represents the coordination sphere. Due to the presence of this coordination sphere, we have compounds called coordination compounds. So you'll find throughout this coordination chemistry, we'll be using this coordination sphere, and coordination sphere will enclose what? The central metal ion and the ligand. This central metal ion and coordination, these ligands, collectively, which are put within square brackets, this whole, this is called as coordination entity, which is one more basic term. Coordination entity. So coordination entity is made up of central metal ion ligands, which you put within square brackets. Then there is an ion outside the coordination sphere, which are called as the counter ion. So all these terms, the central metal ion, the two properties of the central metal ion, one is oxidation number and the coordination number. Ligands, the types of ligands, the coordination entity, and the counter ions will be taken in detail when we study all these terms one by one. The first term, the basic term, is the central metal ion. What is it? It is the metal ion forming the nucleus. Forming the nucleus of a coordination entity. Coordination entity which we put within square brackets. That coordination entity has a central part. That central part you call as nucleus, which is the central metal ion. And what we find, if you observe different types of coordination entities, you'll find that central metal ion mostly is a metal ion of the D block elements. Because it is the D block elements generally which has this specialized property of forming coordination entity. Now there's a reason for that. That reason, you know, there's one more chapter called D and F block elements. In D block elements, you will learn, or you must have learned, that why do D block elements form these coordination entities. So in every coordination entity, there's a nucleus which is the metal ion, and that metal ion is generally, the central metal ion is generally D block element. It's a D block element. Now, these coordination entities are classified on the basis of number of central metal ions. How? One is mononuclear coordination entity. Mononuclear coordination entity. What is it? It's a coordination entity, CEL, right, for coordination entity, which has one central metal ion. It has got one central metal ion. That's called mononuclear. And in our syllabus on coordination chemistry, we will be only dealing with the mononuclear coordination entities, that is the coordination entities which contain one central metal ion. You can have binuclear also. Binuclear coordination entity. Binuclear coordination entity. What is it? It is a coordination entity having two central metal ions. This will not be part of our syllabus in coordination chemistry. And if there are more than two central metal ions, you call it as polynuclear coordination entities, the one which have more than three central metal ions. Throughout our coordination chemistry, which will be dealing only with the mononuclear coordination entities. In the mononuclear coordination entity, this central metal ion, I told you in the beginning, has two characteristics. One is its oxidation number, another is its coordination number. So our next term will be oxidation number. Oxidation number, which I will abbreviate oxidation number of central metal ion. Now first, how will you define this oxidation number of central metal ion? Say if I write the coordination compound CuNH3 4 and outside sulfate. If I take this one, which I had previously written on the board, while I had written all the terms, the basic term which we use in coordination compounds. What is this oxidation number? Copper is the central metal ion, it's mononuclear, one central metal ion. The metal ion which is present within the square brackets is the central metal ion. Now how do you define this oxidation number? If you remove from this coordination compound all these species, the 4 ammonia molecules, you remove them. You remove 4 NH3 molecules as neutral molecules. This sulfate will be removed as sulfate has a charge of -2. What will be left behind? Only what will be left behind will be copper. And how much will be the residual charge on copper? In a neutral compound, the sum of the charges on its various species is equal to 0. Keep that basic thing in mind, because this overall compound is a neutral compound. You are removing 4 neutral molecules, so you are removing no charge because ammonia is neutral molecule. And you are removing 1 sulfate ion which has a charge of -2. So that charge overall is neutral. The residual charge left on copper will be +2. Now you combine them again. 4 ammonia and 1 sulfate will leave you with no charge. So how do you define it? The residual charge left on the central metal ion when all the species are removed from the coordination compound. That residual charge is called as its oxidation number. I will repeat. When you remove all the species from the coordination, it's like you are breaking the coordination compound so that you'll get only central metal ion. So you remove the sulfate, you remove the 4 molecules of ammonia. The residual charge which will be left on the metal ion, which is +2, is its oxidation number. So oxidation number is the residual charge on the metal ion when all the species are removed from the coordination compound. So if you are asked to calculate the oxidation number of central metal ion in a coordination compound, it's a very laborious task that you have to remove all the species from the coordination compound. Then the residual charge left will be equal to 0. Instead of this, there's a very simple method of calculating this +2 charge on copper without breaking apart all these species from the coordination compound. Now what is that? How do you calculate it? How do you calculate the oxidation number of central metal ion? This is our topic, which is calculation of oxidation number of central metal ion in a coordination compound or in a coordination entity. How do you calculate it? We don't know it. We know the metal ion, but we don't know how much is the charge on it. So what you'll do, as an example, what you'll do, the first one, you have CuNH3 4 times within the square brackets, then outside it is sulfate. You are asked to calculate the oxidation number of copper. We don't know it. We'll put it equal to some variable, let it be equal to x. Okay? We'll put it, so we have to calculate this x. What we'll form? We'll form an equation. To this x, which is the central oxidation number central metal, we will add the charge on all the species and equate it equal to 0 because overall this is neutral. It will be 4 into charge on NH3 molecule, 4 times the number of ammonia molecules, plus, and you have 1 sulfate ion, charge on sulfate ion, SO4 2 minus. And since this compound overall is neutral, this sum will be equated to 0. So we form an equation. In 11th class we used to do the same thing. There, instead of taking the coordination compounds for calculating the oxidation number, we used to take simple compounds. There was an element which was having an unknown oxidation number. So we would calculate it this way. Now it's very easy. X plus 4. Ammonia is neutral, so charge is 0. Sulfate is 1. Each sulfate has -2 charge, is equal to 0. And if you equate it, what we'll get? It will imply X will be equal to +2. And I told you, for +2, when you express it in stock notation, as stock notation, we can write it as the second. So in this compound, this central metal ion, copper has an oxidation state of +2. I think it's very clear to you how to calculate the oxidation. So what do I define? I define the oxidation number, the residual charge. Then very simple method of calculating it. You form an equation, put unknown oxidation number equal to some variable, then add up the charge on all the species. If overall species neutral, that sum will be equal to 0, and with the help of that equation, we'll come to know what is the oxidation number of central metal ion. Correctly calculating central metal ion is very important. Why? Because in our next topic, the IUPAC nomenclature of coordination compounds, there in the IUPAC name, you have to mention the oxidation number of central metal ion. And if you don't know how to calculate it correctly, your IUPAC name will be wrong. Okay? So I think you have now learned how to calculate the oxidation number of central metal ion. As an exercise, I'll give some more examples so that you will calculate the oxidation number at home. Before that, I'll give you one more example. Now, this was a neutral species. But instead of neutral, if we have a charged species, like you have FeCN6 3 times, -3, and you are asked to calculate the oxidation number of iron. Now, remember, this is a coordination which is negatively charged. So, the oxidation number of iron and the charge on the 6 cyanide ions, their sum will not be equal to 0, it will be equal to -3. So what you'll do, put the oxidation number, the unknown, equal to X, then add up. Each cyanide has a charge of -1, you already know it. This sum will be equal to the charge on the coordination entity, which will be -3, and calculating this, X will be equal to +3. That means this iron here is in the +3 oxidation state, for which the stock notation is 3rd, this way. One more example will be if the coordination entity is positively charged, like Cr NH3 4 times, Cn 2 times. And this sum will be equal to -1. The charge is -1. Sorry, it's negatively charged. And you are asked to calculate the oxidation number, it's equal to +1. So I dealt with neutral molecule, then negatively charged, now a positively charged. Asked to calculate the oxidation number of chromium. Put it equal to some variable, let it be X. Then add up the charges. Plus 4 ammonia, each ammonia is neutral. There are 2 cyanide, each cyanide has a charge of -1, and this sum of the charges on these various entities will be equal to the net charge +1. Overall, it's not neutral. So in case of positively charged species, you equate the sum of the charges equal to the net positive charge. In case of negatively charged, you equate it equal to the negative charge, that's -3 here. Now on calculating what you will get, it will imply X will be equal to +3, for which the stock notation is 3rd. So it is 3rd. So I have calculated the oxidation number of central metal ion in 3 types of coordination species. 1, the negatively charged, the positively charged, and 3rd, the neutral one. Now as an exercise, you can write these examples and calculate the oxidation number of central metal. So write this question, calculate oxidation number of central metal ion in the following species. The first one is Cr, chromium, NH3 4 times, SCN 2 times, and you have a Cl here. I'll underline this. You have to calculate the oxidation state of chromium. Remember, this is neutral species. Number 2, Co, cobalt, H2O 3 times, Cl 3 times. Overall, this is neutral species. Third, Na, Ag, silver. Here it is cobalt. Here you have to calculate. Now, this is not central metal ion. Why? It's not present within the coordination pair. It's not the, this sodium is outside it. Central metal ion is that which is present within the square bracket, the central metal ion. Ag, Cn, twice. Calculate the oxidation state of silver. The fourth will be Na2, Zn, Cn 4 times. Calculate the oxidation state of zinc. Here. Fifth example, you can do it. Fifth one will be K4 Fe Cn 6 times. Here central metal ion is iron. So you will be asked, I'm asking you to calculate the oxidation state of iron. Sixth one is, these are twin compounds of iron, K4 FeCN6 and K3 FeCN6. Central metal ion, that is copper. So these are some coordination entities, coordination compounds, where you will be, I'm asking to calculate the oxidation number of the central line, metal ion, which I have underlined here. So that was the second term, that is the oxidation number, that is dual charge, and the method of calculating the oxidation number of central metal ion. Now, this central metal ion has one more property, which is this third basic term which you use in coordination compounds, which is coordination number. But before taking up the third term, the coordination number will be we will take up the ligands first, because ligand coordination number of central metal ion is related to the ligands. Now, what are ligands and their classification? This term, the term ligand, it's basically a Latin letter, or derived from a Latin letter, which is liger, the Latin word, from which we have deduced the term ligand in coordination chemistry. Now, what does liger mean? Liger means, it means to bind. And when something binds itself with some other species, that term is called liger. So this ligand must be having a binding ability. The question here is, bind with what? Bind with central metal ion. Okay? So this ligand binds itself with central metal ion. Binding with central metal ion, it forms an entity which you put within square brackets, calling it as coordination entity. But that is just the literal meaning of the term ligand, the binding ability. How do you define this ligand? Ligands are, they can be neutral species, they can be neutral molecules, they can be negatively charged ions, negatively charged ions, or very rarely they can be positively charged ions. It's a very rare that ligand is positively charged. Mostly they are neutral molecules or they are negatively charged. When we take up the different types of ligands, they will find there will be very rare examples of ligands being positively charged. So they can be neutral molecules, can be negatively charged ions, or very rarely can be positively charged ions, which donate an electron pair to central metal ion. Central metal ion has no electrons as to form a bond. Therefore, central metal ion is approached by any molecule or by ion which can donate its electron pair. And by donating it, it binds itself with the central metal ion. That's why the term is ligand. And in our topic on the different concepts of acids and bases in equilibrium, we have already studied one concept, which is Lewis concept of acids and bases. And there, how do we define Lewis base? Lewis base is electron pair donor. That Lewis base in coordination chemistry is called as ligand. Though there are some molecules which are ligand but are not Lewis bases. That's a bit higher. But normally speaking, every ligand has an atom that contains a pair of electrons, and that pair of electron it donates. By donating electron pair central metal ion, it binds itself with central metal ion. So ligands are also Lewis bases. These ligands, they are also Lewis bases. And you know, Lewis base always combines. Lewis base is L, has a pair of electrons. Lewis base will donate this electron pair only when there is an acceptor. And that acceptor is a Lewis acid. It must be a Lewis acid. Why? Because Lewis acid is electron pair acceptor. Which means here, this ligand is donating its electron pair to central metal ion. So central metal ion must behave as a Lewis acid. Which means that the formation of coordination entity is actually a Lewis acid base reaction. Got it? So ligands are Lewis bases. And as you know, every Lewis base has a donor atom. Therefore, every ligand also has a donor atom. Okay? So I'll take examples first. Some examples. Number one, neutral ligands. Examples of neutral ligands. One is NH3 ammonia is a neutral ligand. Nitrogen contains a lone pair, electron pair, which it can donate. So this nitrogen of ammonia molecule can donate the electron pair to central metal ion and bind with it and form a bond. Binding means bond. The atom of molecule which donates its electron pair, that's called donor atom. So in ammonia, nitrogen is the donor atom. In water, oxygen is the donor atom, which has got two lone pairs. It can donate one. It's a neutral molecule. There is a ligand which is NH2, CH2, CH2, NH2. It has got two donor atoms. One is this nitrogen, another is this nitrogen. So two donor atoms. So when it binds to the central metal ion, it simultaneously uses both donor sites or donor atoms to bind with the central metal ion. This molecule is called commonly as ethylene. It's an organic molecule. Ethylene diamine. Ethylene diamine. Because the big molecule, this ethylene diamine, instead of writing this formula, you can abbreviate it as EN. is an abbreviation for ethylene. So they are neutral molecules, ethylene diamine, ammonia, water, they're all neutral molecules. You can have negatively charged ligands. These are neutral. Some of the examples, when we discuss more about the coordination chemistry, I'll be coming up with more examples of neutral ligands. These are some of them. Ethylene diamine, you have water, you have ammonia, neutral ligands. So every neutral ligand has a donor atom. In some ligands, this donor atom can be only one. In a molecule like ethylene diamine, there are two donor atoms. There are two donor sites. Similarly, negatively charged ligand. Negatively charged ligand. Oxygen has 3 electron pairs, so this is the donor. Hydroxide. H negative ion. H negative ion is called hydride ion. Hydrogen atom is not the ligand, but its anion is the ligand. Cl negative ion, chloride ion. This chloride ion has got 4 electron pairs, which I have shown here. One of them it can be donated. So it is again a ligand but negatively charged. You have bromide ion. Bromide ion has got 4 electron pairs. So this can donate one. You have fluoride ion. It can donate electron pair. You have iodide ion. It can donate electron pair. Then there is an ion called cyanide ion. Nitrogen is the donor. Carbon is the donor, sorry. And Nc negative. This is called isocyanate. So C and Nc is a special type of ligand. It has got 2 donor sites or donor atoms. It can bind with metal either through carbon or through, but simultaneously it cannot use both of them. Either through carbon, then you call it as cyanide, and if can bind with metal through nitrogen, then you call it as isocyanide. Okay? Similarly, there are many examples of negatively charged ligands. So because negatively charged ligands are very common, as negatively charged ions are electron rich. Then I told you in the beginning, you can have very rare positively charged ligands. Can have positively charged ligands. One is NO2 with a net charge of +1. Nitrogen is the donor. This is called nitronium ion. Nitronium ion. You can have NO with the net positive charge. Nitrogen is the donor. This is nitrosonium ion. Nitrosonium ion. It is NH2. NH2. This is called hydrazine. But when it is positive, carrying a net charge of +1, then this nitrogen is the donor atom. Then it's called hydrazinium ion. When it is neutral, then it's called hydrazine. But when it is positively charged, then it is hydrazine. So you must have observed one common feature in the nomenclature of positively charged ligands, that all of them end in suffix IUM. IUM indicates that the ligands are positively charged. So ligands can be neutral molecules, they can be negatively charged, they can be positively charged, and all of them have one thing, what they all contain an atom, at least one, which contains an electron pair. It can donor. The atom which can donate electron pair is the donor atom. Now how do we classify these ligands? The classification of ligands. One classification I have already given you, which is on the basis of charge. These ligands are of 3 types. One called neutral ligands. Examples are already with you, like ammonia molecule, like water molecule, like hydrogen molecule. You can have negatively charged ligands. And I have given you many, many examples of negatively charged ligands, like cyanide, like isocyanide, like chloride, like bromide, like iodide. They're all negatively charged. And the third one is the positively charged ligands. The ligands which carry a net positive charge, and they are very rare positive charge ligands. I gave you 3 examples. The nitrosonium ion, NO positive, nitronium ion, NO2 positive, and hydrogenium ion, which is N2H4 with a net charge of +1. So that is also one classification. But this is quite obvious. This type of classification is quite obvious, the charged ligands, because in the definition I define ligands as neutral, positively charged, and negatively. So this classification is quite obvious. Now, how do you actually classify ligands? Is, there is one very important characteristic of ligand, that every ligand contains a donor atom, a ligand, an atom which has an electron pair, which it can donate, also called as donor site. Now, how many donor sites a ligand has? That becomes primarily the classification of ligands. If a ligand has one donor site, then you call it as unidentate or monodentate. Second classification is of ligands is, which is the primary or the main classification of ligands, is on the basis of number of donor atoms. The other name for donor atom is donor site. How many donor sites, how many atoms a ligand has which contains an electron pair that it can donate. Mere presence of electron pair, it doesn't make it a ligand. It should be able to donate it. If it can donate it, then it becomes a donor site. And then only you call it as a ligand. So on this basis, ligands have the following classification. One is unidentate ligands. Unidentate ligands. Uni means mono, means single. Now, why dentate? Why? Because these ligands, donor atoms, are considered as the teeth of the ligands, by which they can catch hold of the central metal line. So they're considered sort of teeth. So if a ligand has only one tooth to catch hold of this central metal line, you call it as unidentate, or you call it as monodentate ligands. You can have bidentate ligands. A ligand which has two donor sites, by which it can hold a central metal line between the two teeth. So ligand has two teeth, two donor atoms, and there's a central metal line. They can donate the two electron pairs to the same central metal line. So they will catch hold of that central metal line using the two donor sites, which are considered as the teeth. So bidentate. Then you have a collective classification, which is polydentate ligand. Ligands which have more than two teeth, which have more than two donor sites, they are called collectively as polydentate. This polydentate will include tridentate ligands, three donor sites, it will include tetradentate, four donor sites. So metal has ligand has four donor sites, and using that donor sites four, it can grip this central metal line between the four teeth. So it will be quite an effective grip on the central metal line if the ligand has more than, say, one donor atom, bidentate, then tridentate, then pentadentate. The maximum sites that a metal has, ligand has, are hexa. So you have hexa, dentate, ligand. So on the basis of number of donor atoms, the monodentate or unidentate, it has got two donor sites, one donor site. These ligands have got two donors, two donor atoms, call them two donor sites. They have got three donor sites. Mind it, if there's a bidentate ligand, it has two donors, but those two donor atoms will be simultaneously used to bind a single metal ion. Then it needs bidentate. A tridentate has three donor sites and using all the three donor heights to bind with the central metal ion. Then only it is tridentate. Similarly, same holds true for tetradentate. Four donor sites. It's got five donor sites. And the maximum donor sites the ligand has got six donor sites. And when it has six donor sites, what does it mean? Six donor sites means all the six will be used to catch hold of a single center metal line. All the six will be donating the 6 electron pairs to a single central metal line. If this is the central metal line and these are 5 donor sites, all the 5 will be donating it to the same central metal line. If it is tetradentate, all the 4 donor sites will be binding with the single central metal line. And if it's a tridentate, all the 3 will be bound with the single central metal line. And if it is bidentate, the 2 donor atoms will be donating the 2 electron pairs to the same central metal line. What I will do, I'll give examples of all bidentate and the different types of polydentate ligands. Number 1, unidentate ligands. The examples of unidentate. Example is ammonia. Nitrogen is the donor atom. I'm showing electron pair. The nitrogen is there. So it has one donor site. Water. Its one donor site is oxygen. It has got 2 lone pairs. But since both the lone pairs are present on one donor site, when it binds with a metal, it uses only one lone pair. So uses one, monodentate. Got hydroxide ion. Oxygen is the donor. The chloride ion, Cl negative. This is the bromide ion, Br negative. The fluoride ion, F negative. The donor site is only one because they are monoatomic ions, so there's only one atom, therefore that atom will be the donor. Iodide ion, I negative ion, there's only one atom, and this iodine will be the donor. The hydride ion, H negative, there's only one atom in it, that's hydrogen, this will be the donor. Then there are 2 very special cases. Cyanide. Here, this is the donor. At that time, this was also electron pair. But what happens? So you'll say that it has got 2 teeth. Why? Because there are 2 atoms in cyanide which have got lone pairs. But when it binds with a metal, it uses either carbon to bind with it or nitrogen. Simultaneously, it cannot use both. Okay? So when you write it as CN, then carbon is the donor. But when you write it as NC, then nitrogen is the donor. Which means this cyanide has an option to bind with the central metal line. This has no option but hydrogen to donate with the metal, to bind with the metal line. But this has an option. It can bind with metal either using its carbon, or if somebody has an option of writing with both hands. When I can write with both right hand as well as with left hand. Like Leonardo da Vinci used to paint with both hands. What are those persons called? Who can write with both hands? They're called ambidextrous. So use the term ambi. Ambi means both. They are monodentate because they have the option of using at a time only one donor. The option is either carbon or such monodentate ligands which have such option. They are called as ambidentate ligands. So among the monodentate ligands, there is a special case of monodentate ligands which are called as ambidentate ligands. The unidentate ligands, that have the option of using more than one donor atom or atom, but one at a time. Example, cyanidine, isocyanide. Now if I take you to the organic chemistry, in organic chemistry, there are attacking reagents called as nucleophiles. Nucleophiles are electron-rich species. They are electron pair donors. There you use the technical term that's nucleophile. Here we use the technical term ligand. There are some nucleophiles which are ambident nucleophiles. And cyanide and isocyanide are taken as ambident nucleophiles. Here they are ligands. But in organic chemistry, they are treated as nucleophiles. They attack the positively charged carbon atom because they are electron rich. But if they have the option of donor, you call them there as ambident nucleophile. Here we call them as ambidentate ligands. So among the unidentate ligands, there is a special case of ligands called as ambidentate ligands. And what is the relation between uni and ambi? All ambidentate ligands are unidentate, but all unidentate ligands are not ambidentate. Like ammonia is unidentate, but it has no option other than using nitrogen as the donor atom. So it's only unidentate, but this is unidentate, has the option of using either carbon or nitrogen as the donor side. So it makes cyanide and isocyanide as ambidentate ligand. Okay, so this is one of them. Similarly, you can have SCN thiocyanate, sulfur is the donor, or NCS isothiocyanate, nitrogen is the donor. So this is again a pair of ambidentate ligands. So these are some of the examples of unidentate, and that a small group of unidentate ligands which are called as ambidentate ligands. The examples also there. The next one was, if ligand has two donor atoms and it can use both them simultaneously, you call them as bidentate ligands. Bidentate ligands. They have two donor atoms that can bind with central metal line. The examples are NH2, CH2, CH2, NH2. I told you This is ethylene diamine. How it is abbreviated as? It is abbreviated as EN, ethylene diamine. It has got two donors to bind with a single central metal ion using its two donor atoms. And here both the donor atoms are same. Such bidentate ligands are called as symmetrical bidentate ligands, where both the donor atoms are same. This is one example. The another example is C2O4 2 minus oxalate ion, abbreviated as OX, oxalate ion. I'll draw the structure of oxalate ion. Its structure is this oxygen and this oxygen. This is one of the structures where these two oxygens are the donor atoms. That means again both the donor atoms are same. It's again like EN. This OX is also a symmetrical bidentate ligand. The third example of symmetrical of bidentate ligands are the glycinate ion, abbreviated as GLY. Many ligands have an abbreviation form. So you need to acquaint yourself with the different abbreviation forms of ligands. Glycinate ion, it is NH2, CH2, COO minus. This oxygen is its one donor atom, nitrogen is another donor atom. So it's bidentate, but the two donor atoms are not same. So what you will call it? When they are same, we call them as symmetrical. But if the two donor atoms are different, they will be called as unsymmetrical bidentate ligand. Similarly, the tridentate, you can have pentadentate, you can have tetradentate, you can have hexadentate. This will be an assignment for you. Please write this question. Give examples of following ligands. Read your book, text. You can give examples. Number one, tridentate ligand. The ligand which has three donor atoms. Tetradentate ligand. The ligand which has four donor atoms. Just have to give an example, at least one. The third will be pentadentate ligand. The ligand which has five donor atoms, and the hexadentate ligand. Okay. Now, among these polydentate ligands, I will take one very important example of hexadentate ligand. The rest you will do yourself. Give example of tetradentate, tridentate, and pentadentate. I'll take up a hexadentate ligand whose structure is also drawn. Hexadentate ligand. It has got 6 teeth. That means it has got 6 donor atoms. The example is EDTA with a net charge of 4. It's an abbreviation. Isn't it an abbreviation form? What does it mean? E means ethylene or ethylene. Ethylene, D, diamine. Tetra, acetate, ion. Ethylene diamine, tetraacetate ion. I'll draw its structure so that you'll come to know which are 6 donor sites. CH2, CH2, N, CH2, C, O, and O minus. One, I'm showing donor atoms here by purple color. This is its one donor atom. This nitrogen is another donor atom. CH2, C, double bond O, O, negatively charged. So this is another donor atom. Similarly, on this side, there's a nitrogen, which becomes its fourth donor atom. And with this nitrogen, you have CH2, C, double bond O, a single bond O minus. It's an acetate ion. Sorry. This oxygen is its donor site. I'm using the purple color for this. This is its donor site. I have CH2, C, double bond O, then this is its oxygen atom, negatively charged, has got 3 pairs, one it can donate. Now count the donor atoms. One is this nitrogen, another is nitrogen, third is this oxygen, fourth is this oxygen, fifth is this 6 oxygen, and sixth one is, it has got 6 donor sites. So it's in hexadentate ligand. Many a times it has been asked, draw the structure of ethylene diamine tetraestate ion and show is 6 donor sites. Out of the 6 donor sites, 2 are nitrogen atoms and 4 are the oxygen atoms. And when it uses its 6 donor sites, it uses all of them to bind with a single central metal ion. All of them are bound with a single central metal. So therefore, central metal ion will be effectively caught by these 6 donor sites, 2 nitrogen atoms and the 4 oxygen atoms. Okay? So these are the classification of ligands, which is the primary classification of ligands, is not on the basis of charge, but is on the basis of the donor sites. 1, monodentate, 2, bidentate, more than 2, collectively called as polydentate. The maximum can be the hexadentate ligands. So that's all for today. Thank you.